Hello, friend. My name is Derek Harder, and today we're going to continue looking at generating images. We're going to look at another technique for generating for creating a latent space, and then when we sample from that latent space, we'll have generate an image that is was never seen before. Okay, so we're going to be looking at generative adversarial networks, or GANs. These are kind of a popular technique. They work a little bit differently than the VAEs that we looked at. So unlike the VAEs, the latent space that's learned or created by a GAN has few explicit guarantees of a meaningful structure. Okay, so it can be much more discontinuous, much more messy. Right. Not to mention, you end up with some things that are very realistic. So they can be very good at doing stuff, but they can be very hard to train and practice. So we'll talk a little bit about that in this video as well. Okay, so let's go ahead and get started. So again, basically it works like this. Okay, so you're going to have, again, two networks, a forger network, or we'll call it the generator again, and a discriminator network. Okay, so this works differently than the decoder. In fact, the generator network is really our decoder here. So the generator network takes an input as like a random vector from a learned latent space and decodes it into a synthetic image. And the discriminator's task is to take an image, and it doesn't know whether it's real or was synthetic, was created by the forger, and it's basically going to learn a binary classification, or it's going to try and determine whether the image was a real one or was created by the generator network. Okay. So an intuitive way of understanding GANs is to imagine that you've got a forger who's working in concert, is working with an art dealer. Okay, so their task together is they want to be able to get the forger to learn his trade so well that he can create forgeries that look like Picasso's that people can't tell are not Picasso, so they can sell them and make a lot of money, right? So the idea is the forger will maybe initially as bad as his task, so he'll create some paintings and he'll mix those with some real ones, and he asks the art dealer to tell him which ones are forgeries, right? And from that feedback about which ones are easily discriminated by the discriminator network as not being real images, so not being real Picasso's, he can go back and change, his weights and his how he creates an image from the latent space to get better at his task. But at the same time, the art dealer, the discriminator, is also improving, right? So it's sort of a feedback loop, right? So we can see on the diagram here. So basically, the way this works is, again, a latent space is going to be learned, but the generator, while we're doing this adversarial process, we will generate vectors at random in our latent space, and the generator will decode those into an image. So then we will feed those images along with a mix of real and fake images. So again, if we were trying to learn how to generate Picasso's, we would have Picasso images mixed in with images generated by our generator network, right? And again, this doesn't have to necessarily be images. So if we wanted to learn Beethoven symphonies, we could have a generator that would decode vectors into Beethoven symphonies, and our discriminator then would try to learn, would try to give a binary result of whether it's a real or a fake, whatever, real or fake Picasso or real or fake Beethoven. And then that feedback goes back to the generator for him to get better at his trade at generating fakes. Okay. Okay, so onto our example here. So before I get into it, so we are, of course, using deep convolutional networks again. So we'll use deep convolutional networks for our discriminator and our generator in this example. We're going to use a data set we haven't used before. So it's relatively big, so you might have problems doing this on your system, depending on what you have. So there's like 200,000 faces in the celebrity face data set. We are going to downscale them to 64 by 64 just to make it feasible that we can actually run this stuff, although it looks kind of pretty pixelated when you go down to that. So, you know, again, schematically, what we're going to have in this example is a generator network that maps some vector of some number of latent dimensions that is a parameter we can specify into an image, so a color image, 64 by 64 pixels. And then a discriminator network is going to take images of that shape and it's going to give a binary score. So basically the probability of whether the image is a fake or a real. Okay. So, and again, this is going to be a kind of a form of unsupervised learning. So we're going to have a custom model and a custom training loop to do this. So we need to chain these together where the generator and the discriminator work together for each epoch. The GAN is going to, you know, the generator generates some images, we mix those in with some real images, and then the discriminator has the results, and we know, you know, so for our loss functions for putting this all together, we know which were the reals and the fake ones, so we can determine how well the discriminator did, and that feedback goes back to the generator to help it improve creating better looking fakes. Okay. So the GAN network maps latent space vectors to the discriminator's assessment of the realism of these latent vectors as decoded by the generator. Right? So the discriminator is going to be trained using examples of real and fake images along with real and fake labels, just as we train any regular image classification model. For the generator, we use the gradients of the generator's weight with regard to the loss of the GAN model overall. So this means that at every step, we move the weights of the generator in a direction that makes the discriminator more likely to classify as real the images that the generator is producing. All right. So, you know, we are trying to train the generator to fool the discriminator. Okay, so before we get into it, just mention a couple things relatively quickly. So, you know, these are just all from practitioners finding out kind of what works best. So, like I think I mentioned, GANs can be very tough to get the balance right. So they can be very tough in practice to get things to work, right? So you need to find a good equilibrium so you don't have the generator or the discriminator end up dominating the other one, right? So they need to kind of stay about the same level of performance so that they can continually kind of improve more and more. So, so some things that apparently work well is, you know, we want to sample points from the latent space using a normal distribution, not a uniform distribution. So randomness is good to get robustness. Because we want a dynamic equilibrium. So, you know, these GANs can get stuck in all sorts of ways. So one way is that we won't always be truthful in the labels that we give the discriminator. So sometimes we will label things as fakes that are real or vice versa. And sparse gradients are usually desirable, but they can hinder GAN training. And I think this has to do with, again, the smoothness of the latent spaces that get learned here. So, so for similar reasons, we did this for the VAEs in the previous video. We really don't want to use max pooling operations, so we're going to use strident convolutions in order to do the downsampling and the upsampling when we do the reverse process of these here. And also using leaky RELUs instead of regular RELU activation. So this kind of relaxes the sparsity constraint here by allowing some small negative activation. That's what a leaky RELU is. So sometimes it can get values a little bit lower than 0. So also, I guess it's common to get kind of checkerboard artifacts. So one way to people find to deal with that is to use kernel sizes that are always divisible by the stride size. But even so, I've noticed on this that still can happen kind of regularly, though, in this example. Also, I won't spend too much time on this, but we're using the CelebA celebrity, so it's a database of celebrity faces. It's relatively big. I think it's the biggest one that we've tried using in this class here. So it has images. But yeah, it's 1.3 gig in size. Uncompressed up to about 1.7 gigabytes. And there's no direct link that I can find. So if you go to this, you kind of have to download it by hand. So and I did use the aligned and cropped images, so I don't know if that was a good or bad thing to do. So there's other ones I believe that are at least unaligned and cropped. But yeah, you have to click on that and go to the image subdirectory, or this is what I did, and download the aligned images zip. So I assume you could also try this with the unaligned. And go in there and get the unaligned and uncropped images. Yeah, well, those might take you to the same place. So anyway, so I was using that zip here. So I just unzipped that in my download it by hand, put it into my data subdirectory by hand, and unzipped it. You probably want to use the quiet option because again, there's a lot of files in there. Let's see how many files are. Yeah, there's over 200,000 images again in this case. So in this example, we'll go ahead and use the Keras util. So by selecting none for the label mode, it will go and find all like JPEG images. I think these were JPEG images. And something's changed a little bit from our textbook. So there used to be a smart resize parameter that you could set, but the correct way to do this now, to use the smart resize, is to use the pre-processing method smart resize. So we take that out of here and add that as a mapping so that it'll map all the images smartly to 64 by 64. So this presumably will crop and resize, preserving the aspect ratio, which is desirable in this case here. So this will probably take a little bit of time to load. Let's go ahead and load these. Yes, there's over 200,000 files that will come in from this. And we're not going to have a layer to do any normalization of the pixels, so we just do that as part of feeding in our data set. So this is going to transform all the RGB values to values between 0 and 1. So since by default there is some random sampling here, each time you run this you should get a different picture, but after they've been resized to 64 by 64, they'll look something like this, right? So it's blown up a bit, quite a bit bigger than 64 by 64 here. Okay, so first let's look at the discriminator and then the generator. The generator. So these are pretty similar to our encoder and decoder from the variational autoencoder. So similar idea, although we're just using a straight sequential and not creating a model yet from it. So it's a sequence of layers here that we'll put together into our final full model here. So we're using the stuff that we talked about. So we're using strides instead of max pooling and leaky RELUs. Another common problem is that generators can get stuck generating things that kind of look like noise. So it's been found that adding dropout in the discriminator can help that. But this has a typical shape of a convolutional network. So, because of the strides, it goes samples, down samples as it's going through the layers here, but we're increasing the number of filters or features to 128. So at the end, we end up with 8 by 8 by 128, or 8,192 here on the discriminator. I forgot to mention then that, so kind of the process here ends up with a latent dimension of 128 on 8 by 8 sized images, but of course we do have to, the purpose of the discriminator is to give a true or false, a fake or real. So we do bring this out to a final dense layer with just one output unit that does a signal. So for the generator, again, these do have to be kind of related, reverses of each other, although it's not quite as obvious as on the previous video how these are related. But we expect to use the same kind of, so we're using 128 dimensions in our latent dimension. So we expect this to come in as something with 128 dimensions, but then we're going to immediately bring that out into an 8 by 8 by 128. So that needs to be equal to the last kind of convolution layer before we do the flatten and make our final decision for the discriminator here. So this is kind of doing that, and then these layers do kind of the reverse. So this brings this out finally to, we should end up with an image that's 64 by 64 by 3 channels from our vector in our latent space here. We're using 128 dimensional here. Okay, so again, you should see that, and you should see that the final output for the generator is going to be a 64 by 64 shaped image when we come in with something that has just a vector of 128 dimensions as input. So finally, we can set up our GAN. We're just going to chain the operations of the generator and discriminator over some number of epochs of training. So again, we're not doing supervised learning, so we need a custom model like we did on our previous autoencoder example. So kind of to summarize what we're doing here, in each step of our training loop, we need to draw a random point in the latent space. So we just create a random 128 dimensional vector, or whatever our latent space size is. So we pass that to the generator, so it will generate an image. So initially that'll be just kind of random. So we'll generate some number of images, and we'll mix those together with real ones. So again, if we're trying to generate stuff that looks like Picasso's, we do want to have a corpus of Picasso images. So in our case, for the celebrity database, we want to generate images in our so we want our latent space to have images that look like celebrities. Right? So we'll mix the generated images with real ones, and we'll add in targets for the discriminator. Although, again, like we mentioned, some of these labels will be incorrect, to add some additional noise in here. So the result after the discriminator is it's going to have labeled some as real and some as fake. So everything it labeled as real, that's what the generator, we want it to try and produce things that the discriminator thinks are real. Okay, so basically, given those, we feed those back into a generator with targets that said, these were all seen as real by the discriminator, and so this part of the loop is where we will update the weights of the generator to move them towards producing output that the discriminator is going to predict are real for generating images. So basically training the generator to try and fool the discriminator. So let's look at the details of this. So again, we need a custom model. We need to have our own custom training step, and also we need to have a compile so that we can have two optimizers. So we need different optimizers for the generator and the discriminator here. We're going to just pass in, those discriminators and generators, like using those examples of just the sequence of layers that we have, the number of latent dimensions that we want to use, and the latent space that we're going to try and learn and create. And we have to keep track of two different losses. So we've got the discriminator loss and the generator loss here. So the compile needs to be overwritten because we need two separate optimizers. So we need a different optimizer for the discriminator and for the generator. So we'll see doing that in a second here. So looking at the train step here. So notice that basically this generates a sampling in our latent space the same size as real images. So we're going to have an equal number of real images and an equal number of fake images. So the generator will generate the same number of generated images as we had real images, right? So by passing in, so this randomly samples from our latent space, pass it in so we get batch size. Our batch size was 32. I didn't mention that before. I think it's 32. So we should have 32 generated images along with 32 real images coming in. Okay? So we can concatenate those together. So now we've got them combined with each other. And we create the labels. Okay, and notice we're doing a little bit, we're adding some noise to the labels here before we pass them into the discriminator for the first time. A little bit different than what I was thinking or said previously. So you'll end up with labels that are, not exactly 0 or 1. So in fact, they could be a little bit lower than 0, a little bit greater than 1. Another thing, I have to think about this. So they concatenate, I was expecting maybe we should shuffle these a little bit. At least the discriminator just learn to always predict the first half as fakes and the second half is real, or however they end up in the concatenation here. But maybe that's not an issue. So for these, but basically these coming in is how we train the discriminator. Okay, so the labels are close to, but just with a little bit of some random noise in here, but they do tell which are the fake ones and which are the real ones from our generator. And we use the usual stuff within a gradient tape in order to capture the loss with respect to the predictions that our discriminator makes, and use that then, whatever the optimizer is that we pass in, for the discriminator, we apply those gradients to get the discriminator to be better. So yeah, this is subtle here, so you follow this. So we're generating another set of random latent vectors, but we're going to say that these are all real images, but actually they're all fake images because we're using the generator again to give all fake images, but we tell the discriminator that they're all real and ask it to make predictions on those. So from that, we get feedback in this calculating the loss here about which ones the discriminator was saying were real when they weren't. Right? Now this loss is going to be with respect to the predictions made here, but we can actually apply those gradients. So these are loss with respect to our generator, though. So we can actually apply those gradients to update the weights in the generator, which is what's happening here. Right? So we're using the other optimizer for the generator to update the weights on the generator trainable weights here. Right? So again, maybe don't get too concerned about the details, but it is both updating the discriminator at one point using outputs from the generator, and it's updating the generator using outputs from the discriminator that came from the generator. Everything is false coming from the generator, but we tell the discriminator that they're all actually real images, and that allows us to get gradients that we can use to move the generator to generate more images that the discriminator will say are real images when they're not. Okay? So tricky, but this basically works. Okay, so before we start training here, again, this is an unsupervised learning. We can tell we'll have two losses, one for the discriminator and one for the generator. So we can tell if they get unbalanced. So if one of them goes to 0, it's being dominated, or it's dominating the other one, right? So that could happen. But what we really want is for them both to stay non-zero, but they'll keep fluctuating up and down. So we can't really tell by looking at the loss whether anything is happening or not, except that they're staying in a bit of an equilibrium, and we're not getting one that's always winning the game that they're playing, the adversarial game. So the only kind of way to do that is to actually output. So at each epoch, we'll use the generator to generate some images, and then we can look at those to see whether, as long as things are staying in equilibrium, to see if the images look like they're looking more realistic or not as epochs go through training. So let's try it out. I'm not going to be able to try this out. So, this will take, even with the GPU, 12 to 24 hours to do 100 epochs here. So I left from the last run that I stopped after 28 epochs here. So you notice, again, they kind of go back and forth. So, hopefully you'll never see anything go to 0. So the discriminator loss stayed around 0.6. The generator loss was 1, went down to 0.9 or so. So they both kind of stayed around those levels here. So you'll end up with images like this. So yeah, this was one of the images, I think, at epoch 25. When I've been training on this one, I stopped a little bit after that. So, the textbook showed some examples of these that came from epoch 30, maybe for the same reason. They didn't really want to wait till a whole 100 epochs. So you get things like this. I presume, we're probably on the right track. So we're looking similar to what we had, what they had here in when we ran it here. So, and I also presume, so if you have time, if you can let it go for more epochs, get it up to 100 or so, they'll start to look even better, right? So, they're recognizably faces. I don't know how much you would say that they're kind of celebrity faces, but that's kind of the idea. It looks David Duchovny-like there. I'm not up on my celebrities, so other people might see some other things in these here. So. Okay, so yeah, let's wrap up for this video here. So just a couple of things that you should have learned from watching this video. So a generative adversarial network consists of a generator network and a discriminator network. So it has a lot of similarity to the VAE that we looked at before. It's a little bit more subtle though. So this adversarial process has to be set up so that the discriminator is trained to differentiate between the output of the generator and real images, so between fake and real. And at the same time, the generator is trained to produce images that can fool the discriminator, right? So both of their weights are evolving in parallel if you get this set up right. So the best you can do is get an equilibrium so that neither the discriminator nor the generator dominates, and if things work smoothly, you'll keep getting results that improve. Both of them are actually improving, even though you can't tell that from the loss, and you'll get more and more realistic output, right? And if you have the time and the memory resources, you can get impressive results from these sorts of GANs. They are difficult to train. It's a dynamic process rather than a simple gradient, right? So you have to get it tuned so you get an equilibrium like I just described here. So there's no fixed loss landscape. So getting these GANs to train requires a lot of heuristics, a lot of trial and error, a lot of kind of reading through other people's what they've done and found out works. So, but they can produce very impressive, highly realistic results. So unlike the variational autoencoders, the latent space they learn doesn't have a neat continuous structure, which has some implications on what they can do. So they might not be suited for doing things like trying to edit an image via that latent space concept. So if you take an image and you want to like make it more Duchovny-like or something, it's going to be tougher to find a vector, a direction to go that will take you in that direction. So, okay, that's it for this video. I hope that was useful for you for understanding how these sorts of generative image generation works, and I hope to see you again later.